Okay, so it's a general technique. Now let's go back to being abstract about it and discuss the two specific objective functions that the NMF algorithm, so this is the specific instance of non-negative matrix factorization that we're discussing, the NMF algorithm. What are the two objective functions that this algorithm can minimize? So really it's a set of two algorithms for two different objective functions. And we'll discuss both of them separately. So first, there's one choice, which is to try to minimize the sum of squared errors. So if we approximate x as a product of the non-negative matrix W and the non-negative matrix H, then we take x and subtract our approximation of it. This is the error of our approximation. And then what this notation indicates here is we take each element, because this is a matrix of errors, we take each element, square it, and then sum it up entirely. So sometimes this is written with an f down here, and it's referred to as the Frobenius norm. So it's just like this squared magnitude of a vector, except now it's for the entire matrix. And that's written more clearly, or more explicitly, but less compactly this way, where we take the ijth element, we subtract our approximation of it, of the ijth element, square it, that's the squared error of our approximation, and then sum up all of the data. So this is one objective that we're going to try to minimize using the NMF algorithm. So this will be one algorithm of the two NMF algorithms. And then a different objective we could try to minimize, which I'll make more interpretable in a later slide, is something called the divergence objective. And so this is also like a distance measure between the matrix X and its approximation WH. And it's written this way. So this will become much more clear in a later slide, but let's just look at what we have. We sum over all of the elements in the matrix. So we sum over I and j of the matrix, the data matrix, the ijth element in the data matrix, times the log of the ijth element of our approximation, minus simply the ijth element of our approximation. So there's no data interacting with this term here, but there is data interacting with this term here. And we sum them up, we take the negative, and now our goal is to minimize this. That'll be a different algorithm, a different NMF algorithm. The nice thing about NMF in general is that it's a very fast algorithm. So these are going to be two very fast algorithms for learning the matrix W and the matrix H. Using something called multiplicative updates. So I'm just going to present the algorithms. I'm not going to rederive them from scratch in this class. The original paper is found here, where they give everything that's necessary in a short 7 pages. However, what their proof does in showing that their algorithm does minimize these two objectives is something very similar to the EM algorithm. So remember that when we want to minimize some function f, so we're in abstract land here, if we want to minimize some function f in the parameter h that can be put into it, one way to do this is to generate a sequence of parameters h such that the evaluation of the objective is monotonically decreasing in that sequence. So NMF does this by doing something called introducing an auxiliary function. So here we have f. It introduces some auxiliary function g. That function looks like this, so we want to minimize something that looks like this. We introduce at each iteration, so at iteration t, a function that approximates it is equal to the function at iteration ht and is convex and also bounded below by the original function. So we get something that intuitively looks like this. And then we, instead of minimizing in an iteration t this function, we minimize this red function in iteration t. And so we can guarantee that we get a better value. Actually, if you look at EM, it's something very, very similar. So this function is like the function L, if you recall from that lecture. The gap is like the Kolbeck-Leibler divergence, and then this function is like the marginal likelihood. So something very similar is being done here. But all of those details are in this paper. For this lecture, we're simply going to go through the very, very simple algorithm that results from that proof. First, we'll discuss the algorithm for minimizing the sum of squared errors. So again, our goal is to minimize this sum of squared errors with respect to the matrix W and H, subject to all of the values in W and H have to be non-negative. So this is what we're trying to do, the optimization problem. The algorithm for doing this looks like this. We randomly initialize H and W with non-negative values, and then we iterate the following, first for H, then for W. The order actually doesn't matter, but we'll show it for that ordering. We first, for every element in H, so the kjth element for all k and all j, we update the kjth element by taking its old value and multiplying it by this gain. So this is why it's called a multiplicative update, because every update to each value in H and W is found by taking the old value and multiplying it by something. And notice that this something is a function of the data matrix X and the most recent value of W, and we just pick out, as well as the most recent value for H, and we just pick out the correct element in those products. So this is something that we evaluate. We pick out the correct elements, multiply them together to get the update. Similarly, for the update of W, we take some matrix products, pick out the correct elements, multiply it by the original value to get the new value. And what the algorithm, what the proof shows is that by iteratively updating H and W in this way, we're continually finding new values for H and W that are monotonically decreasing this objective function. And so we can evaluate this objective function here by plugging in the values for W and H as a function of iteration, and then seeing how the relative improvement that we get, and then terminating when that improvement is small. So here's a more kind of visually helpful, intuitive way of making these updates. So in practice, we can actually update the entire matrices all at the same time in this way. So let's use this color coding, where X is the data matrix, is yellow, red is W, and blue is H, and we're making this approximation. What we do then is we take the original matrix H, we dot multiply it, so this is MATLAB speak for saying take this matrix and do element-wise multiplication. So we do dot multiplication of this, the original matrix H, the old value of the matrix H, with this product of W transpose times X. So we take dot multiplication, element-wise multiplication of this. Then we take this matrix multiplication and do element-wise division of this result. So we do element-wise multiplication, and then element-wise division of that. This entire thing now is the new matrix H. So this requires one line of code. Then on the second line of code, we do this. We take the old matrix W, we do element-wise multiplication of the data matrix X times H transpose, and then that quantity element-wise division by W, H transpose, by this matrix product. So this is the second line in the code. If we want to give this a probabilistic interpretation, it's not necessary or even useful necessarily for this specific objective, we can, of course, view this as saying that we're doing maximum likelihood for a model where the elements of X are Gaussian with this mean and this variance, where the variance in this case doesn't matter, subject to the parameter constraint that W and H have to be non-negative. So this is kind of like what we're doing, because we remember that the squared error penalization is like trying to maximize the log of the Gaussian penalty. Now let's look at the algorithm for minimizing the divergence penalty. So let's look at the multiplicative updates that result from the NMF derivation for this objective. So again, our goal is to minimize an objective. In this case, it looks like this, subject to the non-negativity constraints on the values of W and H. The algorithm, again, randomly initializes H and W with non-negative values, and then iterates with the following updates. These look a little bit more complicated, but again, they can be done in a couple of lines of code where we take the old value in h, we calculate its gain, and then multiply the two together to get the new value of h. And similarly, we do that for each value in h, and then we move to w, and for each value in w, we take the old value and multiply it by some function of what we have. Where again, this w here on this side and this w here is the old value, and then we get the new value. We iterate between these updates. We can evaluate this objective function. It will be monotonically decreasing, and we terminate the algorithm when the improvement is relatively small. So it helps to visualize this one perhaps even more. So let's visualize it in this way. We'll call the purple matrix by definition to be the data matrix X, element-wise divided by its approximation. So WH, remember, is the approximation of X. And so we take the data matrix X and do element-wise division with its approximation. We'll call that matrix purple. Then, to get the update of the H matrix, we take the old H matrix and we do element-wise multiplication with the matrix W, where we normalize the columns of this matrix W. So this is W transpose. We normalize the rows of W transpose so that they sum to 1. And then we do multiplication, matrix multiplication of this matrix with the purple matrix and do element-wise multiplication. Similarly, for the updating the matrix W, we take the matrix H, we transpose it, and then normalize the columns of the transpose, or equivalently, what we would do is normalize the rows of the original matrix so that they sum to 1. And then do matrix multiplication of this purple matrix that we get this way with the normalized matrix, and then element-wise multiplication of the result. So something to notice here that's that could end up making your algorithm not work is that this purple matrix, when we update the blue, when we update H, we need to then update this this matrix here, because H has changed, and therefore this element-wise division has changed. So the algorithm would look something like iterating between updating this matrix purple, updating blue, going back to update this matrix, and then updating red. So perhaps it can be done in about 4 lines or so of code. The divergence penalty is a bit less clear. It's harder to interpret at face value than the squared error penalty. However, the probabilistic interpretation of that divergence penalty that we just discussed is perhaps more satisfying than the interpretation of the squared error penalty. So I have a slide here where I'm going to discuss what is the equivalent probabilistic model that we have that would lead to the same exact update rule as we have with the divergence penalty with this algorithm. So imagine that we have this generative process. We say that the ijth element in our data matrix is a Poisson random variable with parameter equal to the ijth element of the matrix product of W and H. So we take W and H, we multiply them together, we look at the ijth element, that gives us the parameter for the Poisson of the data xij. So remember, a Poisson is a discrete distribution on the non-negative integers. So a random variable x that's Poisson distributed can take values from 0, 1 to up through infinity, but all integer values. And lambda is the parameter. And what we can show is that the expectation of x is equal to lambda. So in a sense, this product, this matrix factorization we're doing, is like learning the expected value for the data matrix under a Poisson generating assumption, likelihood assumption. So if we make this assumption, this modeling assumption, and then we want to do maximum likelihood for W and H under a constraint that they have to be non-negative. What we get is something like this. What we first have that the likelihood of the entire data matrix X given W and H because we make an independence assumption here in this thing, so I'm making an independence assumption, it turns into the product over every element in our data matrix X. So we have a product over all the rows and all the columns, ij, of the likelihood of each element of X given W and H, which can also be written as a product over Poisson random variables where we're evaluating the distribution at a point xij using parameter equal to the ijth element of the matrix product WH. So we have this product. And now we want to do maximum likelihood for this data likelihood. So remember that what we can do is take the log of this likelihood and maximize that instead. And when we do this, what we find is that we get this term here. So the log of the Poisson is equal to this term, where we throw in a constant here to take care of, for example, this term. We have the sum over the logs of the individual Poissons. So this is the log, this term here is the log of this likelihood. We want to maximize over W and H. And then if we add some constant to it, we can show that that is equal to this term here, which is equal to the negative of the divergence penalty that we're trying to minimize. So we want to minimize the divergence penalty. That's equivalent to maximizing the negative of the divergence, which equals this term, which is equivalent to maximizing the likelihood of this Poisson model. So this makes a bit more sense. For example, if we're trying to factorize matrices with counts in them, like term frequency matrices to do topic modeling, the data matrix has integer valued counts, and a Poisson is a natural model for that because the counts could be 0 through 0, 1, 2, up to, there's no limit to how many counts there could be. However, it's very low probability to have high counts, which can be captured by this distribution. And so we're doing maximum likelihood for a model that fits the type of data that we're seeing. So in a sense, this penalty makes more interpretive sense.